All right, so what about an object rolling downhill without sliding, but we want to approach it from a dynamics point of view? Forces and then kinematics afterwards. We can, as we showed up here, we can solve for something using conservation of energy as long as we're taking into account the rotational inertia and the rotational kinetic energy. Or if it's just something simply rolling down a hill instead of something more complicated like a toy car. But what if we want to get into torque? We want to get into that complicated stuff. Well, we showed before in a previous video that you can apply the angular dynamics, the idea that there's a torque on the outside edge of the rolling object due to friction, and that the component of the gravitational force, the sliding component, the sine component, is trying to slide it downhill, but it's not sliding because it has static friction. So there's going to be a torque applied by the friction, but there's going to be a net force on the object from those two forces acting on it from outside. The surface resisting its motion downhill and gravity trying to encourage its motion downhill. So if we write two sets of equations, one for linear dynamics and one for torque, rotational dynamics, we can use those to solve what the acceleration of the object would be. And from that acceleration, we would be able to then do kinematics problems. So let's set up the net force equation. If we do what I typically like to do, which is say anything kind of going to the right side of the page is the positive direction of motion, the mg sine theta going downhill would be positive. So I can look at the net force as mg sine theta minus the force due to friction is going to be equal to m times a. The whole mass about its center mass is going to have some acceleration. And for the torque, in this case, we would typically say that if you have something that's got a clockwise torque, it's going to be the negative direction. But since that's the only torque, let's go ahead and drop the negative signs and just say we're looking at the magnitude of the net torque. And we'd have the force of friction multiplied by the radius of the object would be our torque. And that would be equal to I times alpha. And our little Rosetta Stone that connects these two things, we can say that the linear acceleration of the object would be equal to alpha times the radius. That is going to allow us to solve this problem. Now, as we've probably done in other problems, we've got too many unknowns, right? We've got the friction we don't know, we've got the acceleration we don't know, and the alpha we don't know. That's three different unknowns, but we do have 1, 2, 3 equations. We've got dynamics, the conversion, and the torque. So as long as we do some substitutions and we end up with A equals, we're good. So we're going to start off by getting rid of everything that's not an A. We're going to use this conversion factor to get rid of alpha. Then, since we don't know what the force of friction is, we're not being asked to solve for it, we can use one of these equations to solve for friction and sub it into the other. I'm going to go ahead and do that using the torque equation first. So I'm going to rewrite this formula as force of friction. Let's realize that that wasn't an F, that was an R. Times radius is going to be equal to I times alpha, but we'll solve this and say alpha is equal to A over R. And since it's a solid disk that we were using, I'll put 1/2 mr squared for the I, and then alpha, I'm sorry, little brain fart there, A over R in place of alpha. And we can go ahead and simplify this a little bit. Let's see, if I divide that underneath over to here, I'd have an R squared, and then that R squared would cancel with that one, and so force of friction would be equal to 1/2 m times A. That's kind of simple. The force of friction is half the mass times the acceleration. Interesting. So we can take this now and we can plug it back in up here for the force of friction, and then we can do a whole bunch of algebra. Everybody's favorite thing to do. So if I take my equation 1 there, I'd have m times g times sine theta minus 1/2 m times A equals m times A. And if I add that to the other side, I'd have m times g times sine theta is equal to 1.5 or 3/2 m times a. And if I wanted to solve further, I can cancel the m's out. Another one of those lovely features of something going downhill, that mass seems to cancel out as long as there's no sliding friction causing problems. And let's see, well, I guess mass could still cancel out then. Never mind that last line. So if we go ahead and multiply by 2 and divide by 3, we'd have the acceleration of the object would be 2/3 g sine theta. Now, if we compare that to what we'd expect if there was no friction, and it does sliding, we'd expect the acceleration just to be the sine component of the acceleration of gravity. Sine component's a sliding component. So we're getting 2/3 the acceleration, which means we're not accelerating as fast, or as quickly, or however you want to phrase it, which is great, because we already know from previous problems that when the object gets to the bottom of the ramp, it's going slower. We scroll back up to where we were doing some calculations before. Right here, if we were using conservation of energy, we should expect the velocity at the bottom of the incline to be rad 2gh. But if it's rolling, we'd expect it to be radical 4/3. 1.33 is smaller than 2, so it's slower if it's rolling instead of sliding without friction. And we see down here, sorry for scrolling through oddly there, we get less acceleration than if it was just sliding without friction, so it should be slower again. But anyways, that's some setup of rolling without sliding. Hopefully you find this helpful.